Welcome to The Explainer. Today we're diving straight into the hidden mechanics of the universe. And how are we doing that? Well, we're tackling one of the absolute most grueling, high-stakes academic challenges on planet Earth. We're going to look at the very foundation of matter itself, using a test specifically designed to find the absolute brightest minds out there.
So check this out. What we're looking at is taken directly from the JEE Advanced 2016 paper. Now, this is a notoriously difficult entrance exam in India, one that demands absolute, uncompromising mastery of high-level science. It's literally designed to be brutally tough, with questions spanning the absolute most complex realms of physics, chemistry, and math. I mean, just look at this visual overload. We've got a massive string of mass calculations and electrostatic energy formulas here, all just to find the radius of a single nucleus. The exam is basically asking students to take the measured masses of neutrons, hydrogen, nitrogen-15, and oxygen-15, and then calculate the exact radius of the nuclei. And you have to do all this assuming the binding energy difference is purely due to electrostatic energy. It's just a massive wall of numbers and variables. And, the complexity absolutely does not stop there. We're also thrown into these insanely dense, highly technical calculations just to find binding energy differences. We're talking about dealing with fractions, obscure constants, and radii measured in femtometers. The level of precision required here is staggering. Imagine being a student sitting in that exam hall. The pressure to solve this quickly and accurately must be off the charts.
It just keeps coming. Here we've got this super intimidating setup involving some intense integral calculus. This particular equation, it's required just to calculate the thermal expansion of a wire when one end is heated to 400 degrees Celsius while the other is kept at 10 degrees. It looks totally terrifying, right? You've got complex integrals, changing variables, tricky boundary conditions. But hey, don't worry. Today, we are going to tame this complexity. We're going to find the elegant logic hiding right beneath all these numbers.
Section 1. Beyond Lewis. Enter MOT. So, to survive this exam, and honestly, just to understand the fabric of the reality around us, we need a very specific, powerful theoretical weapon. That weapon is molecular orbital theory, or MOT for short. Now, for a long time, science relied heavily on Lewis structures and valence bond theory. But the thing is, we actually needed MOT because those older theories completely fail to explain real-world observable stuff. Like, for example, the old models couldn't explain why liquid oxygen is actually magnetic. No way they could account for that. They also couldn't explain why certain molecules, like H2, two helium atoms bonded together, simply do not exist in nature. The old rules were fundamentally broken. So we desperately needed a new paradigm. Section 2, Waves of Matter, LCAO. Right, so molecular orbital theory totally changes the game. It tells us that atomic orbitals don't just sit there, confined to their individual atoms when they bond. No, instead, they combine into entirely new molecular orbitals that are delocalized, basically spread out across the whole molecule. And it makes this massive conceptual leap through a brilliantly elegant approximation called LCAO, or the linear combination of atomic orbitals. You see, the famous Schrödinger equation is absolutely incredible, but it really only perfectly solves for single electron systems. For our messy, multi-electron reality, scientists have to use LCAO to mathematically combine the wave functions of different atomic orbitals, usually in a head-on orientation along the bonding axis. I know, that sounds super complicated, but the analogy for it actually makes it really beautiful. Just think of it exactly like physical waves in a pool of water crashing together. Since these orbitals are literally described by wave functions, they end up interacting with each other in the exact same two specific ways that actual water waves do when they meet. Section 3, Bonding versus Antibonding, the Dance of Electrons. Okay, so this wave interaction creates two completely distinct types of molecular orbitals out of the original atomic ones. We call them bonding orbitals and antibonding orbitals. Let's break down exactly how this dance of electrons works. When the waves combine in phase, they reinforce each other, right? This is your classic constructive interference. It actively increases the electron density between the atom's nuclei, creating a lower energy, highly stable bonding orbital. But on the flip side, if they combine out of phase, they essentially cancel each other out. That's destructive interference. It creates this region of literally zero electron density, which we call a node, right there between the nuclei. This forms a higher energy, destabilizing antibonding orbital. Scientists actually mark these with a little asterisk just to signify their volatility. And that brings us to the absolute golden rule of molecular orbital theory, bond order. The formula itself is wonderfully simple. It's just 1/2 of the difference between the number of bonding electrons and the number of antibonding electrons. That's it. This single, simple little formula is basically the master key to unlocking molecular stability. If the calculated bond order is positive, boom, the molecule is stable. If it's 0 or negative, like we saw earlier with He2, then the molecule simply cannot exist. Section 4. Putting theory to the test. Acing the JEE Advanced.
All right, now that we've got this foundational knowledge under our belts, let's zoom back out to our high-stakes arena. Let's see how this actually cuts right through the fog of a highly complex chemistry problem from that 2016 paper. First things first, we rely on a core rule from the NCRIT 11 chemistry textbook. It perfectly reminds us why all of this actually matters in the real world. You see, MOT finally explains the magnetic properties of reality based entirely on how these electrons pair up in our wave orbitals. If there are unpaired electrons just hanging out in those molecular orbitals, the molecule is paramagnetic, meaning it physically reacts to magnets. But if all the electrons are neatly paired up, it's diamagnetic.
So here's exactly how we defeat the JEE question. The exam asks students to evaluate all these multiple tricky statements about bond lengths and energies. But by simply sketching out the molecular orbitals and applying our handy 1/2 formula, you can effortlessly find that the O2 2+ ion has a bond order of 3, while a standard O2 molecule has a bond order of 2. And because a higher bond order always means a tighter, shorter bond, we immediately know for sure that the O2 bond length is greater than O2 2+, just like that. We can also quickly prove that N2+ and N2- both have bond orders of 2.5 and that the helium-2 ion actually has less energy than 2 isolated helium atoms. By just mapping out the waves, what initially looked like an impossible memorization task turns into a really simple logical puzzle.
Section 5. The Blueprint of Reality. Waving goodbye to solid truths.
You know, mastering this fundamental building block of nature really proves something incredibly inspiring. It shows us that even the absolute most intimidating, high-level science, the exact kind that makes up the hardest exams in the world, can totally be broken down into elegant, logical rules once you have the right perspective. So I'm going to leave you with this final provocative thought. We used to think of atoms as these hard little spheres with hooks on them, right? And for a long time, that was accepted as a solid truth. But molecular orbital theory came along and showed us that the very atoms making up our entire world are actually just interacting waves of probability. If the most solid things in our reality are literally just crashing waves, what other supposed certainties in our universe are just sitting there, waiting for a new theory to rewrite them? Thanks for joining me on this explainer, and as always, keep questioning the world around you.